So let's recap a little, meaning summarize where we've got so far. We're in the process now of trying to show that the set of all possible languages is not countable, it's uncountable. Now we've proven in the previous session that the set of all Turing machines is countable. So if we can prove that the set of all languages is uncountable, therefore there must be more languages than there are machines, Turing machines. And that means there must be languages that are that have no corresponding machine. There must be languages that are Turing unrecognizable. So that's the bigger picture. So now we're trying to show that the set of all languages is uncountable. And as an intermediate step in that process of proving that, we introduced the set B for binary, and that set, it contained, yes, an infinite set, and each member of that set, big B, was a string of infinite length and a binary string. Okay, so just an infinitely long binary string, just a string, with zeros and ones. All right. Well, what we're going to try to do now, the strategy is the reason why we introduced that B, the set of all infinitely long binary strings, is we are now going to prove, and virus is still playing up, irritated throat. We will show that just a minute. Just a minute. Interesting. My wife's, Saturday, she slept in, just woken up, and left her study door open, which I closed. I just find it incredibly distracting if I even think that she's listening, but she wasn't. She was not in her study. Anyway, now I've got to get back to the left brain. So we're going to use this intermediate step, this B, and we're going to show that in fact there is a bijection, there is a correspondence between the set of all possible languages, and let's label that the set of all possible, and I'll call it capital L, italic L here. So this L here is the set of all languages, well, over the same alphabet, over an alphabet, big sigma. Now, what we're going to show is that this set of all possible languages over this alphabet is actually bijective with the set B. Okay. Now, if B is uncountable. Now, did we show that? No. Did we show B is uncountable? I don't know if we actually did that. It was not explicitly done. So there's another gap in so maybe I need to spell that out. If I had to prove So it says here that the bottom line of the previous session, we will show that B is uncountable by using a proof by diagonalization, similar to that used in theorem 4.17. So where is the actual proof? I don't remember writing that. I don't. Because B is uncountable. It's just assumed. It's not proved. Okay, there's a gap. There's something missing in Sipser's proof. Well, let's try to. Let's well, maybe for him it's so obvious. Another one of his jumps. We can now, if you go back to his diagonalization proof, well, Cantor's diagonalization proof, and there we had 10 different kinds of digits, right? Because we were talking about decimal digits, and we proved that big R is uncountable. Well, let's take a special case and not have 10 different digits, we want to have 2. So then our infinite, the reals then, in a sense, become, the set of reals becomes big B. Okay? Because now you've got, instead of having an infinite string of decimal digits, you now have an infinite string of binary digits. You only have 2 symbols, not 10. You only have 0 and 1. And you can use this. You can do the same argument, the same diagonalization trick. So you can represent each real, I suppose, as a binary number. You can convert a real into a binary number. It's just changing the representation. Okay, and then you just do the same diagonalization trick as before. So I guess I'm assuming that kind of idea is so obvious to Sipser that he feels it should be obvious to you as well. But if not, I hope you've followed my reasoning. You can readily adapt the diagonalization argument with decimal digits to binary digits. So then your set big R, set reals, gets replaced by this set big B, right? The set of infinitely long binary strings. Okay, but it's the same argument. Okay, so bottom line, B, set of infinitely long binary strings, is uncountable. Okay, B is uncountable. File that away. Now, what we're going to try and do now is show that the set of all languages, big L here, and B are, in fact, there's a bijection between them. There's a correspondence between them. And from that means they're the same size. Okay, so that means, given that B is uncountable, therefore L, this L here, must also be uncountable. Okay, so that's what we'll try to prove now. Now, if L is uncountable, that's the set of all possible languages, whereas the set of all Turing machines is countable. Therefore, there must be some languages that don't get paired off with a Turing machine. There's just no Turing machine for that language. So some languages are not Turing recognizable. There's just no machine for them. There are not enough machines. Okay, so what we'll do now is finish off proving that there is a bijection correspondence between L and B. How to do that.